and we march on confidently toward what should be another test. Not an exam for you, but an exam where we get to determine whether or not an infinite series converges or diverges. Such things are important. And just to give you this sense, as we move on in the unit of study looking at infinite series, it is very rare, very, very rare that we will find for the whole rest of our 3 weeks. It is very rare that we are going to find a sum of a series, but we will spend a lot of our time determining, does a series have a sum? And so this is one way for us to determine, does a series have a sum? In fact, I'm going to give you 2 ways to determine, does a series have a sum? One I'm not going to spend a lot of time on. It's the direct comparison test. And I'm not going to spend a lot of time on it because of the other one that I am going to spend a lot of time on. The direct comparison test goes like this. Let A sub n be some series of non-negative terms, and let B sub n be some sequence. Sorry, A sub n is a sequence. Should not misspeak. A sub n is a sequence of non-negative terms, and B sub n is a sequence of non-negative terms that is at least as big as the A sub n's for sufficiently large n. And all that means is maybe the first few terms, maybe the first 10 terms or the first 2,000 terms or whatever, the A sub n's are bigger than the B sub n's, but eventually B sub n takes off and is bigger than A sub n forever. If the sum of the B sub n's converges, then the sum of the A sub n's converges, and if the sum of the A sub n's diverges, then the sum of the B sub n's diverges. This is one of those things that actually makes sense if you think about it. I know this is school, so we don't think. Let's pretend that the A sub n's are these dots like so. And let's pretend that the B sub n's are these dots. It has to be the same. Like so. Okay? What does it mean for the B sub n's to converge? For the B sub n's to converge, it basically means that if we were to add up all the areas of all these little rectangles here, if we were to add up all those numbers, it would approach a sum, a finite sum. Well, if we add up all these little rectangles and we get a finite sum, and all of the red rectangles are below those, then the red rectangles have to get closer and closer to a number. They can't shoot off to infinity. Similarly, if the A sub n's diverge, if I add up all of these rectangles and I get infinity, and the B sub n's are bigger, they have to approach infinity also. So, show that the sum of the series 1 over radical n times 3 to the n converges. Now you could write out terms for this for 3 days and not see a pattern at all, but you should see this. What do you know about the series 1 over 3 to the n? Well, it's geometric. You could write out terms, 1/3, 1/9, 1/27, 1/81. Common ratio is 1/3. So it converges. But I don't think it's too hard to imagine that this is less than or equal to that. I mean, we're multiplying the denominator by something that is at least 1. So this fraction must be less than this fraction, or at the very least equal to when n is 1. So I have a sum of a sequence that is less than a sequence whose infinite series converges. So the series we want converges also. Okay? Okay. I'll show you one more. Show that the sum, as n goes from 1 to infinity, of radical n over n minus 3 diverges. Well, in this case, I want to compare with this series. What do you know about that series? You should think very carefully Yes, I should speak very carefully. You should think very carefully about what you know about that series. That's a P series. It diverges. P is less than or equal to 1. And since P is less than or equal to 1, this series diverges. Do I have to convince you that the series we're interested in must be greater than that? Do I have to convince you of that? I hope not. And since this series is greater than this series, so it diverges also. Okay. Now, I don't want to spend a whole bunch of time on that because I have something better. I have the limit comparison test. Also called the law of looks like. I had a calculus class name it that several years ago. It's the law of looks like, and it looks like this. Let A sub n and B sub n be sequences of positive terms. If the limit as n approaches infinity of the A sub n's over the B sub n's is any number that isn't 0, then both series, the sum of the A sub n's and the sum of the B sub n's, converge or both diverge. They do the same thing. Whatever the one does, the other does. And this is much more useful to us because, going back to here, because if this n minus 3 is an n plus 3, then we don't have this inequality, and so we can't use the direct comparison test. But if this n minus 3 is an n plus 3, we can use the limit comparison test. And if the n minus 3 is an n minus 3, we can use the limit comparison test. So I'll show you what it looks like. Show that the sum of the n squareds over n to the fourth minus n minus 1s converges. Should probably use plus 1. Show that that series converges. And to show that that series, oh no, not that, color, there, go that color. I'm going to make a comparison with the sum of the 1 over n squareds. for two reasons. One, I know it converges because it's a p-series and p is greater than 1. But the other reason is that if I squint, this already is 1 over n squared. I mean, if I squint, if I let n get really big, these terms don't matter. Only the lead terms matter, and they reduce to 1 over n squared. So if I do that, if I take the limit as n approaches infinity of the one over the other, I'm going to get the limit as n approaches infinity, copy, change, flip, n to the fourth over n to the fourth minus n plus 1. That's a number. That's a number that isn't 0. And since that's a number that isn't 0, then whatever this series does, this series does. Therefore, the sum of the n squareds over n to the fourth minus n plus 1 converges. Must be. Must be. One more. What about, here, let's leave it open-ended. What about the sum of 1 over radical n squared plus 4? What about that? Well, what am I going to compare with? I'm going to squint. And if I squint, this doesn't matter, and I get 1 over radical n squared. Well, that's 1 over n. And we already know what that does, don't we? It's a p-series, where p is less than or equal to 1. This is the harmonic series. This diverges. So if we take the limit, it then approaches infinity of the one over the other. This is the limit of copy, change, flip. And that's 1, which is a number which is not 0. And since this is 1 and not 0, whatever this series does, this series does. Thus, the sum of the 1 over n squared plus 4s also diverges. Now, we could not have used the direct comparison test here because these terms are not bigger than the 1 over n's. So we can't say, oh, these are the blue dots above the red dots. These are different dots. Okay, your turn. I want to know if certain series converge or diverge. What about the sum of the n cubeds over n to the fifth plus 4n plus 1? That's an interesting question. What about the sum of the 1 over radical n cubed plus 2n minus 1? What about the sum of the 3n plus 5 over n times n plus 1 times n plus 2's? And what about the sum of the n cubeds over radical n to the 7th plus 2n squared plus 1's? Do they converge is the question. Okay, so those are some things for you to consider. We'll talk about them when we get together. My 15 minutes are almost up, and so there you go. Thanks, everybody.